where, and it's hard to see, but the satellite starts here and goes up here and then comes back down here and goes up here and then comes back down there. And so that's kind of the shape of that satellite as it's moving through. And let me see if I can find a better one. Maybe it's got a better color than that. Well, that's was that. Can anybody see? That's hard to see, but there's a line right there. And that says 10, and that says 11. So it's at 10 o'clock, it's here, 11 o'clock, it's here. And this is where it is above the Earth. Now, 10 o'clock, it's here, and 11 o'clock is here, and then it goes all the way over to here, and there's 3, 4, 5, and then at 9 o'clock, it's there. So in 24 hours, it goes from this side to this side in 24 hours. That means it rotates around the Earth once a day. Or does it?
I thought it was twice.
It goes twice a day. But here it's only once a day, right? I'm starting here and I end up over there. Ah, now the Earth is spinning, right? So it then starts from the west and goes to the east, right? Now the Earth spins this way, right? It spins this way. It spins this way. Right? And now this is starting in the west. So as one rotation of the Earth, the satellite has to go around twice. Because it's going the other way, west to east. Now if it was like a stationary one, like up by the sun, and just sat there, then it could just sit there and it looked like it goes around the Earth once. Because the Earth's going to rotate, but it's essentially stationary. Because the sun's like a big satellite sitting right there. It's stationary, but it looks like it goes around the Earth once a day. So, the concept is, these satellites go from west to east, and they have to go around the Earth twice to get this apparent one rotation per day, or revolution per day. Okay, make sense? So, physically, it's going around twice a day, but because the Earth's also rotating in the same direction once a day, it only is apparent that it goes around from the sky once a day. Okay. Now, what's the point of that? Well, the other point of that that's shocking to me is those things are about 12,000 miles up there, and they're going around the Earth twice a day. You can figure out how fast they're moving? Yeah, they're moving pretty doggone fast. Hundreds of miles per hour. And we got to figure out where they are, to like in a meter, in a second, to get our accuracy. I mean, that's just mind-boggling to me that those things are moving so fast up there, and we can figure out where they are and where I am to within a meter, as those things are just flying by. Okay, that's enough of that. That's not enough of that. There's more stuff in here. What's actually on here neat now is that we have other satellites popping in. Here's the GLONASS satellites. So they've got a lot of satellites. I'm going to change this back to Knoxville. Hang on, city, Knoxville, select, and change this back to 10 degrees. I'm not getting to my guidance system stuff, guys. You know, I'm supposed to do that. Okay, so these are just my my GLONASS satellites. I still have the hole in the sky because it's got an orbital plane. I also have a hole in the southern sky too. I mean, if I was in the southern hemisphere, there'd be a hole to the south. But if I turn that off, the other thing is, hey, we've got Galileo satellites up there. Woohoo! Oh, only two. Now, those are not IGNOS satellites. Those are Galileo satellites, and that's the Galileo system. They only have 2 satellites up there. They're trying to get 20 or so, and they're rotating around the Earth. So it's not the differential correction system, which is Europeans' IGNOS, which is the SPAS. It's the European GNSS, which is the Galileo system. It's only got 2 satellites running right now. Compass, which is the Chinese one. They only got one up there too. So they don't have that many. They do have some geostationary satellites over in China, but some that are rotating around the Earth, they don't have that many. And the WAS satellites, no, we only got 2. and they're not moving. Well, those are those geostationary SBAS, differential correction satellites, and they're supposed to be stationary. They're not supposed to be rotating. It's just for us. So, of the systems that we have up here, these four, GPS, GLONASS, Galileo, and COMPASS, are the GNSS systems. Two, in effect, GPS and GLONASS. Two that are sort of just in development, Galileo and COMPASS. The European one and the Chinese one. The only differential correction system that we have up there for satellites is just WAS, and it shows it there. Now, that's kind of important to us, because where are these satellites? In the southwest sky for WAS. And how low are they? For us, they're like 30, 29, 28 to 40 degrees. They're fairly low in the sky. Point to the southwest. You mean armpit angle about 40 to 30 degrees? And that's where that satellite is. So the blockage of our WAS satellites, it happens a lot. So for WAS satellites, we're losing differential correction pretty significantly. I'm not happy with WAS about that. And there's some and they've actually changed their satellites numerous times. Where's that? Yeah. See, they've changed their they put them on different satellites that are up in the sky. They don't have their own WAS satellite. They just buy time off of these other satellites. Deer does the same thing. Okay, that's enough of this stuff. You guys done with this? So I wanted to show that to you for a couple of reasons. One, to show you the DOT thing. The other one is to show you the GLONASS types of satellites up there. Anything else that's neat up here? Those that have done Trimble stuff? You can identify things. Healthy satellites. You can look at the ephemeris values, I believe, in here. Yeah, this is the, not the ephemeris, but the almanac values. So this is the almanac value for PRN number 4, its eccentricity, square root of the semi, and there it is, the argument of the perigee. And then all this other, the rate of the right ascension. This is the Keplerian orbital parameters that are used to describe satellites that are rotating around the Earth. Okay. Not the ephemeris that's used for calculating your position. And you can get this from the websites. You can go to the website and say, download a new almanac, because you need to download new almanacs periodically. Make sure you're not reading off old almanacs. All right, that's enough of that. Any questions on that before we move forward with guidance systems? Well, let's talk a little bit about guidance systems. What kind of guidance systems are there? What are the two distinctions between guidance systems?
Like a light bar that you follow and then one that actually drives through.
Exactly right. You have what's referred to as a guidance system, or they refer to as a parallel swathing or a light bar that you have to drive. It guides you. It helps you. Provides guidance. The other one is referred to as an auto steer system. It's a hands-off unit. It takes over. It drives around the field by itself. So those are typically the two different styles. And in the handout, this is actually what's in the text. One uses the light bar or some sort of visual display of where am I supposed to drive, and then you have to follow that light bar. Now, there are two ways to set this up. I'm going to introduce this right now. One is you set up the light bar so you follow the light. If the light's over to the left, you drive to the left. Okay? Follow the light, like a moth. The other one is like you need to correct the light. If the light's too far to the left, I've got to turn back the other way to get the light back to the middle. And you can set up your light bar different ways. So if you're used to one, and then you get one in, and you drive it, and you're following the light, and you end up curling around the field, that means it's set up wrong for you, and you can go in and reset it up. So they use a light bar. A lot of the new ones